Welcome to this video on what I think is a very interesting result and topic in calculus known as L'Hopital's rule. And for this rule, recall that the limit as x approaches a for f of x divided by g of x, if we end up in a situation where the limit as x approaches a for that numerator function f of x is equal to 0, and the limit as x approaches a for g of x, the function in the denominator, is also equal to 0, then we get a case where we are taking 0 and dividing by 0. And we've developed what's known as the indeterminate form. 0 divided by anything is 0, but dividing by 0 makes it undefined. We don't really know what's happening with this particular value. Now, when you initially looked at limits, you probably were able to address this by maybe factoring the two functions and canceling something out. In a case with square roots, multiplying by the conjugate of an expression. If there's trigonometry involved, maybe using a trig identity. And it's also possible for certain functions that if you simply graph them, you might be able to figure out the limit visually. All great ideas. But here comes a little bit of a history lesson in here. In the late 1600s, Guillaume de L'Hopital was presented with an idea by another mathematician named Bernoulli. He was presented with an idea specifically to address this case where you end up with the indeterminate form when looking at limits that result in 0 divided by 0. And so before we get into this idea and how L'Hopital addressed it, we have to first look back at what's known as the limit definition of the derivative, which is the formal statement for what a derivative is. And how all derivatives are defined is the limit as h approaches 0 for f of x plus h minus f of x all over h is equal to f prime of x, or the derivative of f. And that definition just shows that if you take 2 points along a curve and let the distance between them go down to 0, you are left with the slope of a tangent line, the idea behind the derivative. Now there's also an alternate form to this definition that you need to be aware of, which states that the limit as x approaches a for f of x minus f of a all over x minus a, still looks very much like a normal slope formula, is equal to f prime of a, which is specifically the derivative value for a function at any x value that we're calling a. And that's the one that we got to be familiar with before we get into L'Hopital's main idea. And so let's go back from the start of this video and bring back a couple pieces of key information. We're dealing with the limit as x approaches a for f of x over g of x. And we're setting up the premise that the limit as x approaches a for f of x is 0, and the limit as x approaches a for g of x is also 0, creating the indeterminate form. So what we'll do first is we'll take that limit expression and rewrite it as the limit as x approaches a for f of x minus 0 over g of x minus 0. Haven't changed the value at all. This is certainly equivalent. But notice, with our starting information, if the limit as x approaches a for f of x is 0, that implies f of a is equal to 0. Same with the limit as x approaches a for g of x. That implies g of a is equal to 0. Which means equivalently, I can rewrite my limit as the limit as x approaches a for f of x minus f of a all over g of x minus g of a. And that notation starts to look a lot like this alternate limit definition of the derivative. I'm just missing this division by x minus a. And I can solve that problem really quickly by multiplying the top and bottom of this expression by 1 over x minus a, which creates this new limit expression. The limit as x approaches a for f of x minus f of a over x minus a, all divided by g of x minus g of a over x minus a. And what the limit definition says is that this will be equal to the derivative of f, f prime of a, over the derivative of g, g prime of a. And what we'll do to wrap this up is kind of reverse the limit substitution that we are used to from past limit problems. And I can rewrite this expression as the limit as x approaches a for f prime of x over g prime of x. I've simply unsubstituted the a value in place of the x. And if all of these expressions are equivalent, this must mean that the limit as x approaches a for f of x over g of x is equal to the limit as x approaches a for f prime of x over g prime of x, on the basis that the original limit for f of x and g of x were both equal to 0, which is the idea that became known as L'Hopital's rule, specifically for evaluating limits that result in the indeterminate form. Because notice one of my key steps in establishing that proof was that f of a equaled 0 and g of a equaled 0. Without that, this rule wouldn't exist. So a very big finding that connects some of the differentiation you're used to doing back to limits. And in application, this is a relatively straightforward rule to apply if you are comfortable with basic differentiation rules. So let's look at a couple examples before we wrap up. The first example, let's set up the limit as x approaches 0 for sine of x over x. Notice in this problem, the limit as x approaches 0 for sine of x is equal to 0. So the numerator will result in 0. And the limit as x approaches 0 for x would be 0. So 0 in the denominator as well. That is the indeterminate form, which means L'Hopital's rule can be applied in this case. And what we do, we can rewrite this as the limit as x approaches 0 for the derivative of the numerator, sine of x becomes cosine of x, over the derivative of the denominator, x becomes 1, and we can try to proceed with direct substitution. And substituting in 0, we'll get cosine of 0 over 1. Cosine of 0 is 1. 1 divided by 1 gives us our final overall answer. The limit as x approaches 0 for sine of x over x, in the end, is equal to 1. Now make note on this, we are taking derivatives of a fraction, but this is not the quotient rule. Quotient rule is still your method for differentiating a quotient of two functions to get a new derivative function. L'Hopital's rule is saying that by differentiating each individually, I can create a new limit that would be equivalent to the original. Very different, and we want to make sure we do not get L'Hopital's rule mixed up with quotient rule. They apply in two very different types of problems. Let's look on one more example. For this one, we'll look at the limit as x approaches 4 for the square root of x minus 2 all over x minus 4. Again, the first thing we have to notice is why L'Hopital's rule is going to get applied. The limit as x approaches 4 for the square root of x minus 2 by direct substitution would result in 0. And the limit as x approaches 4 for x minus 4 by direct substitution would also be 0, which means this is the indeterminate form. Now if that type of problem looks familiar and you realize, well, I could multiply this by the conjugate and try to solve it through that way, yes, you absolutely could. But if you're comfortable with differentiation, this saves some time and helps you avoid some unnecessary algebra errors that could pop up. So, if we know L'Hopital's rule can be applied, we will end up with the limit as x approaches 4 for the derivative of square root of x minus 2, which is 1/2 x to the negative 1/2, all over the derivative of x minus 4, which is just 1. Simplifying that expression down so we can go ahead and do our direct substitution, that whole thing would be equivalent to 1 over 2 times really x to the 1/2, which we can rewrite as square root of x. And now, by direct substitution, we will get 1 over 2 square root of 4. And overall, the limit for our original problem has a finite value equal to 1/4. And that's it on L'Hopital's rule. Again, the only big considerations to make, this can only be applied in cases where you get the indeterminate form, 0 over 0, and making sure that even though you're starting from a quotient of two functions, you are not confusing this process for limits with the quotient rule for finding derivative functions. Thank you for watching.